Okay. So again, we continue the basic counting principles, more examples. So today we are going to look at a very interesting question to start with. It's called the northeast lattice paths. Okay. This is going to be a very useful idea, and it could help you come up with many different proofs in nice ways, many combinatorial proofs for several of the things that we are going to look. Okay. So this is as follows. So the one question that we want to look at is as follows. You have this grid, okay? So on this grid, you are allowed to move from the origin, let's say 0, 0, it's called the origin. You are only allowed to move either to the right, from wherever you are standing, right? You can go to the right, or upwards. You know, you are standing, let's say here, let's say here, you are not allowed to go down, or you are not allowed to go left, right? These two are not allowed. So at any position, you can go either to your right or upwards. So this is called northeast lattice path because we consider the upward movement as north movements and right movement as the east movement, right? In a map, usually that is the convention that we follow. So this is called northeast lattice path. Now, the question is that suppose I start from 0, 0, right? And then I want to go, let's say 1, 2, 3, 4, 5, 6. And then I want to go 1, 2, 3, 4, 5 up. Okay, so I want to go to the 6,5 grid point, right? So you can assume it's an infinite grid, but we are only going from 0, 0 to 6, 5. Now, how many different ways you can go to 6,5 starting from 0, 0? That is the question. Can you solve this? Can you count the number of ways you can go from 0, 0 to 6, 5 using only north or east movements, right, from this grid? So think about it for a few minutes and then continue with the lecture, right? So let me give you how to count this. So how many ways we can how many steps we need to reach 6,5, right? So we definitely need to take 11 steps to reach 6,5, right? Because I definitely need to make 6 right movements before I can reach the column number 6, and I need to make 5 top movements before I can reach the y coordinate with 5, right? So the row number 5, right? So to reach 6,5, I definitely need to make exactly 6 right movements and 5 top movements or north movements. And I don't have any other possibility, right? Because if I go one more left, there is no left movement allowed, right? Or one more up, I cannot come down because there is no down movement allowed. So therefore, I have to only move right or left. And since I have to take exactly 6 right steps and 5 up north steps, I know that I have exactly 11 movements. No matter which route I am going to take, I am going to make exactly 11 movements, right? Now, I have 11 possible movements. Now, out of these 11 possible movements, 6 of them must be east movements, right? Or right movements. And 5 of them must be up movements or north movements. But suppose I decide which are the right movements I am going to make. Right? I say that, okay, here I am going to take a right movement. Here I am going to take a right movement. Then he will say that, okay, I am going to make a right movement here. and then a right movement here and a right movement here, right? Then you know that yeah, or maybe here also, right? The right movement here, right? So once I decide which are the precisely the 6 right movements I am going to take, the other up movements are pre-decided. There is no choice, right? Because if I want to make the right movement here, then I know that I must have moved up here and also here. There is no choice. I also must have moved up here, and up here. So these are without any choice. So therefore, the moment I decide the 6 right movements, my 5 north movements are decided. So therefore, I just need to decide the 6 choices out of the 11 possible movement options. So 11 choose 6. Okay. So 11 choose 6 possibilities are there. Or instead I can choose the up movements. The 5 possible ways. So 11 choose 5. Both of them will give the same number because we already know that 11 choose 5 is equal to 11 choose 11 minus 5, which is 6. Therefore, I have 11 choose 6 or 11 choose 5 possible northeastern lattice route from 0, 0 to 6, 5. You can replace 6, 5 with any number and you will get the arbitrary m, n lattice paths, right? This m plus n choose m or m plus n choose n. Now, using this now, we can easily ask some further questions. For example, I will say that, okay, instead of this, I'm going to need the paths I can make starting from 0, 0, going to this particular point, right? Maybe maybe these paths are representing some one-way streets in some some weird city, right? Where you can only move north and east movements, right? And there is happen to be a very famous bakery, right, at this position B, right? So I want to, I start from my office, let's say at 0, 0, and going back home. But then I'm going to visit this bakery to buy some stuff from there. No, it's not healthy. Maybe we don't want bakery. We want something else, right? Some vegetable shop, maybe, right? So I want to buy some fruits or vegetables from here, and then I want to go home, right? So then I want to say that, okay, I want to stop from my office at this place. Now, how many ways I can go from here to home if I am guaranteed that I will stop at this particular shop? So try to come up with an answer by using the previous methods that we know and the one that we just found out. Now, here is a question that algorithm people will be very interested in. For example, like you have a matrix product, let's say n plus 1 matrices are there, m1, m2, m3, etc., mn plus 1. These matrices are to be multiplied as m1 into m2 into m3 into etc., mn plus 1. Now, this matrix multiplication, of course, it's not commutative, so I cannot arbitrarily change the order of this thing. So I have to keep the order of the matrices. But now, when I do the multiplication, I can only multiply 2 matrices at a time, right? I cannot multiply all of them together, right? So I have to multiply 2 of them. Then, I can multiply this multiplied number with something else, right? In the next one in that order, whatever. Or I can instead, like I say that I multiply m1 and m2 first, then I multiply m3 and m4 first, then I multiply m1, m2 with m3, m4, the product of m1 and m2 with product of m3 and m4, right? That is possible. Or maybe, I can just multiply m1 and m2 first, find the answer, then multiply with that with m3, then find the answer, multiply the product of these 3 now with m4. So there are several ways I can do this product. To find the same product, There are several ways I can do this, and some of them may be more efficient than the other, depending on the type of matrices that we are looking at. But without looking at that, we want to say how many different ways I can do the matrix multiplication. So find the number of ways to parenthesize this product so that I can find different ways of multiplying this. For example, let's say that you have, let's say, 4 matrices A, B, C, and D. Okay. So if I want to multiply A, B, C, and D, I can first, let's say that, I will say that, okay, I multiply A and B first, right? Then I multiply C and D. Then I multiply the product A, B, and C, D. So this is how I give the bracket, right? Then I can also say that A, B, C, D I take. I multiply A and B first, then I multiply with the C, then I multiply with D, right? So this is the second possibility, right? I want to just separate them out so that it doesn't look like the same thing. We will just extend it here. Okay, so then what are the other possibilities? Well, A, B, C, D I have. Then I multiply, let's say, B and C. First, and then I multiply with A with B and C. Then I multiply with this product with D. This is one possibility. Or I can multiply C and D first. Then I multiply with it with B. Then I multiply with A. This is another possibility. Any other possibility? I multiply, let's say, A and yeah. So what is the other way? There is another way. Maybe I multiply with the so I multiply B and C first, then I multiply it with D, right? Then I multiply with A, right? So this gives a different order, right? So here I multiply A and B, C and D separately, then multiply them together. Here I multiply A and B, multiply it with C, product, and then multiply that product with D. Here I do BC first, then A with BC, and then that product with D. Here I do BC first, then BC with D first, and then A with the product. And here I do CD first, then B with CD, and then A with BCD. Now I have found out 5 different ways. Can you find more? Maybe there are more, I don't know, right? So you figure out if there is any more or if it is the exhaustive list. Now, but I wanted to find out for general n plus 1 matrices or whatever number, right? So I just put n plus 1 for some reason, but that is not really important. Now, the interesting thing is that to find out this, we can use the idea of the lattice paths that we were looking at, the North-Eastern lattice paths. Okay? So, if you have n plus 1 matrices, then you are going to put n pairs of brackets, right? That we saw. Like we have 4 things, right? Which is 3 plus 1. So I put 3 pairs of brackets, right? For the product. So I put 2 together. So therefore, you need 1 less. Okay? Because there is going to be exactly whatever the number of terms minus 1 products happening, right? Number of products is exactly 1 less. So therefore, that's why you have 1 less bracketing. So you are going to put parentheses now, n parentheses to define this product. But that is precisely saying that how many different ways you can put parentheses so that the you always have the number of parentheses on the left more than the number of parentheses on the right, because if otherwise we are going to be in trouble, right? Because when you want to balance it out, we want to go from the left, right? So we want to find the balance parameters uh, and count how many of them are possible if there are going to be n parameters. So we want to find the total number of balance parameters where there are n of them, right? N pairs of them. Now finding this is going to be uh, reducible to counting a type of path from origin to n comma n, right? You want to find n pairs of brackets and find the number of balance parameters that is possible with this. It is basically counting the number of paths from 0 0 to n comma n, okay, with some property. Now can you think of what is the property that we are looking at, right? We want to look at the paths, the northeastern lattice path starting from 0 0 to n comma n, but we want to make sure that this will give the total number of balance parameters. So again, stop and think about it for a few minutes before you look at the answer, how to do this. Sorry. So here is how it is going to be. Okay, so I want to start from the 0 0, and I want to produce paths which reaches n comma n. Right. Now let us say that my right movement is going to denote a left parenthesis, and an upward movement denotes a right parenthesis, closing parenthesis. So opening bracket and closing bracket. Okay. So the right movement is a opening bracket, then the upward movement is a closing movement. Now, when I start from 0 0, I have to make a movement. But now, whenever I put a parenthesis, I have to start with an opening parenthesis before I can put a closing parenthesis. So only after I move a right movement, I can go upwards. Now, can I go again upwards from here? If I go upwards from here, what happens is that I am going to put another right parenthesis. But then this is no more balanced, right? It cannot be balanced because if you are going just to the right, you can never add things to the right. You cannot now if you make a movement here and then here, what you are going to do is to do this and this. This is not going to make the parenthesis balance. So therefore, I always need to make sure that the number of left parentheses is never more than the number of right parentheses that has appeared so far, right? I mean, never less than the number of right parentheses appeared so far. Or in other words, when we are making the movements in the lattice, we cannot cross the main diagonal. 0 0 to n, and there is a diagonal. Because if you are going to cross that diagonal, that means that we have made more upward movements than the number of rightward movements. So therefore, that will say that the number of right parentheses is more than the number of left parentheses that is used so far, which means that the balancing the parenthesis is not balanced. It's not going to be balanced. So therefore, I want to find out roots from 0 0 to n comma n that does not cross the origin but only makes right and upward movements. So I want to count the number of such paths. Now the question is that can you count the number of paths from 0 0 to n? So so we know that all such paths we counted that, right? Is n plus n, right? Which is 2n. Choose n, right? M plus n, choose whatever m or n, which is n plus n, choose n, which is 2n, choose n, right? So we know that total number of lattice paths without looking at the diagonal, total number of lattice paths is 2n, choose n, right? Total number of northeast paths. But now we put the condition that it cannot cross the blue diagonal, right? The main diagonal that we came up with. So it must always lie below it, right? Not that it shouldn't cross, it should be below it. Because the left parenthesis must be more than the right parenthesis before we, not strictly more than, at least as many as the right parenthesis, right? So how do you count now the guys who doesn't go up, right? So we want to find the guys who doesn't go above the diagonal. So can you count this? So think about this for some time. In fact, yeah, I would even recommend that you think about it for even a half a day, or something like, spend some time thinking about this before you look at the solution. So let me tell you what is the solution I can come up with. There could be other ways to solve this. There are actually other ways to solve this. And what I am going to do is to use our well-known subtraction principle, which means that I am going to find the bad guys and remove them. I think that is easier to count. Okay? So I am going to count the bad guys. So what are the bad guys? The bad guys are the paths which crosses the diagonal, right? It goes above the diagonal. So I want to count the northeast and lattice paths which goes above the diagonal at some point. Okay. Or maybe I don't want to erase this. Okay. So suppose some path goes above the diagonal. Then it must cross the diagonal at least at some point, right? Now the first time it crosses the diagonal, I mark that point as special. So you take whatever your path is, right? Your path may do like this, right? Or it might even go further. Then it might go right, again maybe right, then go up, right? Maybe this is one of your paths, right? Or maybe you started in another way, right? You started maybe right itself, then went up, but then went up again here, right? Then you went right, right. Maybe you went right, then you went up again here, maybe up again here, then you went right. So this path also cross the diagonal here, right? So these are the bad guys, right? We don't want such paths, right? Now, can you count these kind of bad paths in a different way? You might ask, like, okay, what is the difference in counting the one which is below and then the ones which are crossed ones, right? Now, there is a difference, we will see. So what I am going to do is a trick. So the trick is the following. So every bad path, which means the path, the path that crosses the diagonal, crosses it for the first time, right, somewhere, right, along this path. Okay. So the moment it crosses, I mark that point as special. Okay. Now what I am going to do is that I am going to reroute this path by doing the following. Okay. So after the point, till the point it crosses, I will not do anything. Okay. After the point cross this, right, exactly once, right, the first time it crosses, any path, the remaining path, I will look at the remaining path and say that, okay, anytime it goes us to the right, I move upwards. Okay. So I'm going to continue this path as follows. So instead of going up, right, I am going to go up. Okay. The next movement is again right, so I again move up. Again, the next movement is right, so I again move up. Okay. Now, then the next movement is where it is going upward, so therefore I move right. Okay. Again up, therefore right. I should not use this thing. I will use the dot just to make sure it is the virtual path that I am creating, right? So again, 3 upward movements. So therefore, I am going to make 3 right movements. Then I am going to right again here. So therefore, I make an upward movement. Okay. So there must be something here. So I will extend my infinite grid to this. Okay. So then, so once I made this movement, I have reached this point, right? Somewhere, whatever. What was that point? It is the point I moved n plus n minus 1 comma n plus 1, right? Someplace, right? I reached. Okay. So I did this. So after it crossed once, I decided, okay, wherever it was going right, I'm going to go up. And wherever it is going up, I'm going to go right. Right. Now I do this for the every path. Okay. So the red path that we were looking at, for example, right, cross here. Now since it crossed here, it was going up, and then next movement was up, so instead I will go right. Okay. Then the next movement was right, so instead I will go up. Again the next was right, so I will go up. Again the next was right, so I will go up. And then the next was up, therefore I will go right. So I happen to reach n minus 1 comma n plus 1 again here. But the claim is that every path, after this, switching, right, of the things after the thing, will always reach this point, particular point. So all the bad paths, I can do this, idea that, right makes left, and, like the right movement becomes the upward movement, and the upward movement becomes the right movement. So this is basically what we are going to do, is precisely looking at this diagonal. Okay. And we are going to reflect the path, which is above this with respect to this diagonal. Okay. I'm looking at the reflection of the path. So this path was like this. So now it has, with respect to this diagonal, its reflection is going to be like this. Similarly, this path, its reflection is going to be like this. Now the claim is that every such reflection will come to the point n minus 1 comma n plus 1. Can you think why? So why does the reflection always reach n minus 1 comma n plus 1? Okay, you need to answer this. Okay, because if I give all the answers, there is no fun, right? But it is easy. So think about this. All the reflected paths will finally reach this point n minus 1 comma n plus 1. So we only reflected the bad paths, right? We are going to count the bad paths. So every bad path after the reflection reaches this point. And now every path from 0, 0 to n minus 1, n plus 1 on this grid, right? This subgrid, I mean not sub of the original one, but this grid that we are looking at, right? Right. So every path from 0, 0 to n minus 1 comma n plus 1 on the grid corresponds to a bad path after the reflection the other way. Okay. So instead of doing this way reflection, I take the other way reflection, right? Right becomes, I mean, the same rule, but take the reflection of the paths going from 0, 0 to n minus 1 comma n plus 1. They will all reach n comma n, and they will all cross the main diagonal at least once. This is something you can observe and see, and try to answer why again. Okay. So why? So why the reflected path always reaches here, and all the paths to n minus 1 comma n plus 1 reaches back to n comma n, and all such reflected paths will have crossed the diagonal at least once. Okay. Now, once you have this observation, right? Once you have this, you can do the counting, because we are saying that we look at all possible paths starting from 0, 0 to n comma n. And which are the paths which crosses the diagonal, it goes above the diagonal. Those are the paths which after the reflection reaches n minus 1 comma n plus 1. And we said that there is a one-to-one correspondence between the paths that start from 0, 0 to n minus 1 n plus 1 and the bad paths from 0, 0 to n comma n which crosses the diagonal. Right? Because every such path gives a bad path here, and every bad path always reaches here. Okay? So try to explain why this is true, okay, and convince yourself it is the case, and then we have the answer. So we have 2n choose n possible total paths from 0, 0 to n comma n, and then going from 0, 0 to n minus 1 comma n plus 1, we have n minus 1 plus n plus 1, choose n minus 1, right? These are the bad paths, right? So I can subtract. So this is going to be equal to 2n choose n minus 2n choose n minus 1. I think I made maybe 2n choose n minus 2n choose n minus 1. Okay. And you can use either your algebra or some other nice arguments. Think about this, whichever way you want, to finally show that this quantity is going to be equal to, again, right, 1 by n plus 1 into 2n choose n. Okay. It's going to be 1 by n plus 1 into 2n choose n. So show this, and we get the answer. And this number is very, 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 very important. Okay? It has a special name. It comes as solution to so many combinatorial questions. There are even books on this. So it's called Catalan number. Okay, so if you look at Richard Shanley's book on enumerative combinatorics, he lists some 400. The updated edition has some 400 or 500 combinatorial questions to count things, whose answer is going to be the Catalan number. Right? So many different areas, so many different things it comes from, and all of them finally boils down to Catalan number. So it's called Catalan in the memory of mathematician called Catalan number. So it's usually right with C capital, so it's the name. So this is the number 1 by n plus 1 into 2n choose n. Okay. So Catalan number we just found out is the number of ways to parenthesize the n plus 1 matrix. Okay. Right. Product to do a multiplication. Right. Or it is a number of ways to do the balance parentheses with n pairs of parentheses. And it is a number of paths starting from 0, 0 to n comma n, right, which does not cross the main diagonal, right, which stays below the diagonal, right. So all these things are, of course, Catalan number already. Now we can find so many other things. So think about some other situations where you can think of Catalan numbers.